to the review. Lecture 3. Closed system. We started on first law of thermodynamics for closed system. First law for closed system. Net minus work net equals energy stored in the system, right? And we solved a couple problems by using work calculation. What was work? Work, the integration of P and D, right? And then we defined polytropic process. Basically, P times with the power of n equals constant, right? If n equals, it is different thing, 1, P2, V2, that's P1, P1, 1 minus n. Right? N equals 1, work will be, these are work will be equal to P1, V1, natural log of V2 over V1. This is basically what we did in the previous lecture. Today, we will start properties of pure substance. And state postulate. State postulate states that the number of independent properties needed to completely define the state of a thermodynamic system is one more than the number of possibly relevant work interactions. And we need a simple system for this. Simple system is a system is one where there is only one possible relevant work interaction. For example, expansion or compression work. Okay? This is the simple system. That's what our interest in thermodynamics is for this level. And what is state postulate for a simple system? State postulate for a simple system. For a simple system, only two independent properties are needed to completely define the state of the system. Remember, in our first lecture, we defined what properties are, and we said we have extensive properties and intensive properties, right? And specific property, the property of extensive properties, right? Per mass. So in thermodynamics, we assume system is simple, and state postulate says, in order for us to determine what we have in the system as a property, we only need two properties with one condition. They have to be independent of each other. So some properties are dependent on each other during the process. Let's run a simple experiment and show that on a TV diagram, temperature versus this rolling diagram. In our experiment, I have a closed system. You can consider this as a pan of water. Water, pan filled with water, right? With a closed distance member assembly. We have water inside, let's say.
I'm sorry, like a water tank or?
Water tank,
Okay.
it's a closed system, distance member assembly in this case, right? But we have water inside. Heat is applied externally. Change the phase of the water. And we apply heat gradually. temperature versus specific volume. What happens when I apply heat? The temperature increases while the piston increases, right? Let's say at a 25 Celsius at room temperature, and I increase temperature by applying heat. Increases, increases, increases. The point where it needs to change phase starts boiling. What happens when I change the phase? Temperature stays constant. Temperature stays constant for 1 atmosphere. Let's say this is P atmosphere, right? What is the boiling temperature of water? It's around 100 Celsius. When I boil, evaporate every single molecule in that container, I increase the quality of vapor, which makes it superheated vapor. Okay, I get into another region, and in that region, temperature keeps increasing. Okay? All right, and this is at a pressure 1. Experiment 1. If I run the same experiment at a different pressure, everything is same. I will just change my pressure. Heat. Right? I just add extra weight on top of the cylinder, double or increase the temperature. What happens in that case is that it starts increasing temperature and specific volume. But this time around, my saturation temperature, meaning boiling temperature, is different, right? It's higher because my temperature, pressure is higher, and after boiling starts constant temperature because of phase of change. Same thing happens here. Ignore this. So if I keep doing this again and again, again and again, what I have is this. Right? And this is for pressure 2, which is higher than P1. And this curve is called saturation curve. Okay, let's talk about in details what these regions are and what the saturation curve means on a PV and PS diagrams, PV, or other diagrams. Okay. All right. Let's talk about PV diagram first. PV diagram. Pressure versus specific volume for the wall. pressure bar or kilopascal. Saturation curve in a PV diagram. It looks like it leans towards the pressure side. The purpose to draw it down. Okay. Here, this line is saturated liquid line or locus. Line or locus. Some books, some references use locus instead of a line. Okay. This is saturated vapor line or locus. Start point, critical point, where I pass from liquid to vapor superheater region directly without going through transition. Okay? Okay. We have 3 more regions shown on a PV diagram. I will just draw a new one to make it simplified. I don't want to make this confused. Okay. The same graph, you can use the same graph, but I will use a different one. This right-hand side, left-hand side of the saturation curve is called compressed liquid region. Okay. Right-hand side called super heated vapor region. And under the saturation curve is wet vapor region. Wet vapor region.
So when comparing that with the linear lines that you drew, I'm guessing that like the critical point represents like a phase change, or is that what the critical point represents?
So we started that experiment in the compressed liquid region, where we have everything liquid, right? And we increase the temperature, right? We got closer to vapor phase, closer and closer. So this line is saturated liquid region, right? Saturated liquid line. So when we keep that line, we start changing phase. we start creating vapor molecules. Okay? And under the saturation curve, it starts developing and increasing vapor temperature. Okay? And when we hit on this line, everything is in vapor phase. We don't have any liquid. And when we keep adding heat more, we increase the superheated vapor. We still have vapor, but we increase the energy of that vapor. Okay? Okay, let's show process lines. Remember, we had a couple processes which we defined during our definition, concept and definitions. Process lines, we have a specific way of showing them on a PV and PV diagram. Okay, process line. And a PV diagram. What were they? We had isobaric process, isometric, isothermal, adiabatic. Isobaric processes. What was isobaric process? Where pressure is constant. Okay? And we're still talking about that experiment we run. Pressure versus specific volume. Specific volume. Pressure in bar or kilopascal. Specific volume. Saturation curve. For the first experiment, my pressure was P1, right? It was at atmospheric pressure. And for isobaric process, when you show a PV diagram, it will look constant. Right? P1. It will be either this way or that way. Depends on the process takes place. P2 higher. Both constant. P2 constant. P1 constant. Isometric process or processes. Again, specific volume. versus pressure. Oh. The constant volume for first experiment, V1, constant, could be either way. Arrow pointing upwards or downwards. We'll talk about that. It's just the process now, isometric process. You will see them solve problems. For second case, constant. In this case, V2 bigger than V1. Isothermal processes. This volume. Pressure. Constant temperature, isothermal process, the constant temperature. And so I have T2 and T1, they're both constant, and T2 is higher than T1. T1, right, temperature on a PV diagram, these diagrams, okay, it's 3D in real life. But what we do in thermodynamics, usually, we take 2D slides of that 3D and plot. So, but it's hard to read from a 3D application. Okay? So it is P temperature, pressure, specific volume, and temperature, 3D. Okay? So what I'm showing here is just the 2D of that 3D diagram. Okay? So temperature, right, which has the one axis of that 3D diagram, will look like this. Okay? It's relatively linear when it comes to liquid side. Constant under the saturation curve. Quadratic and superheated region. T1 constant. It's a constant temperature line on a PV diagram. For higher temperature, right, this is not quite right. This should be horizontal. T2 constant. adiabatic processes. Just volume, pressure, adiabatic process. There's no heat entering or leaving the system, right? Insulated system. So in that case, we have a steeper curve. Steeper curve. Like this. This is adiabatic process. Now let's talk about how we find and determine those properties as the part of this diagram. Okay. The equations of states. Equations of states are actually I use to find my property for that specific state. Equation of state relations among three thermodynamic properties.
Is that three?
Three, right? Oh. Temperature, pressure, and volume. Right? There are a couple of ways to find those properties, but we will try to use the simplest one because it's already complicated. We can use, okay, let's say maybe use, they might be determined by algebraic equations by using physical relations between those three properties, temperature, pressure, and specific volume or volume. But as you can tell, they're not linearly related. Changes depends on the region where you are on, right? If you're in a compressed liquid region, they behave differently. If you're in a superheated vapor region, they behave differently. And it depends which one is constant, which one is various, so which makes things even more complicated. But you can find by using algebraic equations. Okay, it's possible, but it's quite painful. Or they can be found by using graphical plots or sketches. But there are shown on a 3D plots, temperature, pressure, and specific volume usually. And those graphs, I will try to find an example and show you. They're not nicely curved. So those curves and the pressure side is different and temperature side. And when you look at from a temperature pressure side to find a specific volume, it's quite hard to find an exact property. Okay. So what we're going to use in this lecture, third one is a tabular. Basically, there are tables available outside. You can find those properties. Okay. So someone in the past have found those properties, measured, keeping the pressure constant, keeping the temperature constant, find the specific volume, when the specific volume is constant for all three regions, and they tabulated those values for users, for the future users. Okay? Because the system is saying the property, pure substance is saying water is water, right? Ammonia is ammonia, whatever you need to use. Okay? So that is what we are going to use, tables. And those tables are available on accounts, right? You can find them under file, tables. We're going to use two types, SI units and US customer units. So the next lecture, we will start how to read those tables. Okay, please make sure you bring your tables with you. Okay, and we will go through those tables together next class. Okay. All right. Steps. And using property tables. So each table has a specific name. For example, table A1, table A2, table A3. And the first step we will do will determine the substance. Like water, R22, R134A, ammonia, etc. After determining the substance, we will need to determine fluid condition. Fluid condition. Is it compressed liquid? Is it saturated liquid? Is it wet vapor? Saturated vapor? Or is it superheated vapor? Right? So the next step depends on our fix. Action depends on results of previous steps. Let's call this one A, one B, C, D, and E. Okay. If B or D And in saturated liquid or saturated vapor, assume the first known property is pressure. If the second known property is temperature, and its value matches the saturation value, you don't have two independent properties.
What's after value? I don't know.
Its value matches the saturation value. You don't have two independent properties. Remember state postulate. You want to determine the rest of the properties, you need two independent properties. Okay? And therefore, cannot determine the state of the system. So assume the first known property is pressure. The value of the second known property except temperature, because of the reason we just described above. Exactly matches saturated liquid. It is shown as F fluid on the table. For saturated vapor, G stands for gas. Value of that property. condition of the fluid as saturated liquid or saturated wafer. Saturated liquid B wafer D. Value of second known property matches saturated liquid or saturated wafer volume corresponding known pressure or temperature go to appropriate saturation table. And read all properties directly from table. Okay? Either saturated liquid F or saturated vapor D. Can see it, right? Okay, under the file, tables, you have two different property tables. Okay, you can either use this one, and you can either use these two together. This one, saturated liquid temperature table, saturated vapor pressure table. Okay, so let's go to any of them. Let me show you other one too. Okay, for SI units, let's talk about water, or you can use this one as well. Okay. Table A2, the properties of saturated vapor, liquid vapor temperature table. Okay. This table is as a function of temperature. Go to the next one, table A3. Okay. It's the same table, but as a function of pressure. If the pressure is constant, table A3, if temperature is constant, table A2. So we say, if you have, after determining your properties, right? Water, ammonia, R22, R133A, and we have other pure substances. You check your saturated liquid values and saturated vapor values. If you are standing on those lines, left line or a right line, right? If you have the exact value, either in specific volume, internal energy, enthalpy, or entropy, you determine where you are depends on the values you have, right? After comparison. Okay. We said go to appropriate saturated table and read all the properties directly from the table, either saturated liquid or saturated vapor. For example, go to table A2 or go to table A3. Okay. This is an example of, this is an example, of course, the water. Go to table A3 or go to table A2. Okay. In this case, it's temperature and pressure. Action depends on results of previous step. What if we don't have saturated liquid or saturated vapor? What if we have wet vapor? If C wet vapor region volume second known property is between saturated liquid F and saturated vapor G. While it's corresponding to known pressure or temperature. Please make sure you bring your tables. Right. But where do I stand between those lines? Am I closer to saturated liquid or am I closer to saturated vapor? I'm between, yes, but I might be anywhere. So I need to calculate that. Okay. And depends on the location of that line on the saturation curve. That pure substance has a quality. And what I do here, what I'm going to do here is calculating that quality of that pure substance, okay? Which will determine the position of the state. Calculate quality from second known property. And corresponding saturation molecules. What is quality? Quality is the mass fraction of the mixture that is vapor. If the mixture is full of vapor, the quality is 1. If you don't have any vapor, quality is 0. Okay, so it ranges from 0 to 1, 0% to 100%. The quality factor shown with X as calculated from second known property for specific volume at the mixture minus specific volume saturated liquid divided by saturated specific volume difference between a saturated vapor and saturated liquid. Okay. If I have internal energy as a second known property, it's U minus UF over UG minus UF. If I have enthalpy, it will be H minus HF over HG minus HF. Entropy will be S minus SF, T minus divided by S, T minus SF. Huh? If I have E, which is superheated vapor. If the value of the second known property is greater than the saturated vapor, the vapor volume, corresponding the pressure or temperature we need to go to appropriate table. Go to appropriate superheated table and read other properties using linear interpolation. If it is necessary, sometimes it is. So superheated tables. Let's talk about water again. Okay. I come to this table A2 and A3 for saturated liquid and saturated vapor values. And the one I have is higher than saturated vapor values. I go to superheated vapor tables. It should be next one. Okay. Whichever the source you use, it should be the next one. Okay. So for, in this case, it's table A4, properties of superheated vapor. Okay. They're tabulated as a function of pressure. For that pressure, in this case, it's 0.06 bar or 0.006 megapascal. Okay, this gives you a saturation temperature, which is from the previous table, and knowing your second known property, specific volume, internal energy, enthalpy, and entropy, you determine your other properties. In this case, you can determine your temperature. okay, by using linear interpolation. Linear interpolation is just finding the fraction of that value property. Okay? We will go over this again and again for the rest of the semester. Okay? This is very crucial. So the other table I showed you, it might have different pressure values here. Notice it doesn't show every single pressure value. And sometimes it doesn't change linearly as a function of pressure. So in that case, you might want to go check the other table. That table might have the pressure values this table doesn't have. Okay? Goes up to 30 bar. Goes up to 300 bar. It's quite enough. What if I have compressed liquid? Compressed liquid. What if I have compressed liquid? If the value of the second property is less than saturated liquid value, corresponding to the known pressure or temperature in that case the fluid is in compressed liquid region. For compressed liquid region, compressed liquid tables may not be available. If it is available, you go to compressed liquid table and read the corresponding value if you need. But most of the case, you will not find compressed liquid tables. Even if you find, even if it's available, it will not give you a wide range of temperature or pressure. It will give you 50 Celsius and then jump to 200 Celsius, okay? Or it will give you 2 bar and then it will jump to 20 bar, right? So it will not give you detailed tabulated values. So if the compressed tables, let's put it that way, if compressed tables are not available, use approximation. That in the compressed liquid region, this volume, internal energy, enthalpy, and entropy is a function temperature only. Okay. And properties. May be approximated as those of saturated liquid at a given temperature. Any questions? That's all for today. Right? Please make sure you bring your favorites. I'll see you next Tuesday.